Welcome back to topic 8.6, Gauss's law, daily video number 2. In this video, we'll apply Gauss's law to planarly symmetric examples. My name is Eastman Landry, and I teach at the Kinder High School for the Performing and Visual Arts in Houston, Texas. Let's start by looking at a brief review of charge densities. In particular, we have 3 different ones we're going to talk about. One of them is linear charge density, which is lambda, charge over some length. And when we take the integral, it's going to be of the integral that we give you, but integrated by dr, or some dl length term. On the flip side, we can also have an area or a surface density that's signified by sigma, which is a charge over area. And that one ends up being the equation that's given to you, but integrated over the surface, or that dA, the differential area element. Lastly, we have our volume density, which we say is rho, Q over V. And that one, sure enough, is going to be our total charge, which is our volumetric density integrated over that differential volume element, that dV. So just kind of keep these in mind as we stop through these next problems. Also, when we look at planes of charge, such as this one here, the E-field lines might look something like that. They create edge effects. Think about being in a room for people that are all packed together, picking up their arms. They all have to be pretty much straight up. But if you're near the edges, you might be able to spread your arms out a little bit. Electric field lines are doing the same thing because they're not allowed to cross. Well, here's a fun little note. For the AP exam, by default, you should ignore edge effects, because from the setup, we're going to make edge effects be negligible. How do we do that? Well, we either zoom in really close to a sheet like we have here, which is making them all look pretty parallel, or we pretend that it's an infinite plane of charge, which doesn't really exist, but if we have it, it would also do the same thing. So we call this a parallel or uniform electric field that's going to look like that. So keep that in mind as we're solving these planarly symmetric surfaces, that our electric field lines are always going to be uniform. So let's look at an example to kind of put this to work. If we have a conducting plate that has a surface charge density of 23 nanocoulombs per meter squared on it, what's the E field going to be inside that conductor? What's that, you say? Yeah, it's just 0, because any conductor in electrostatic equilibrium is going to have an electric field of 0 inside of it. Why? Well, let's look and we can prove it. All the charges are going to exist on the top and the bottom of that surface. They kind of move around to make that happen. If we look at Gauss's law, then, if we look at our charge enclosed, we need to look at our Gaussian surface to fix this left side. Well, if we make a Gaussian surface inside of our conductor, there's no charges in there. And if there's no charges inside of our conducting block, that would also mean that our electric field by definition has to then be 0. So that's why it's 0. There's no charges in there. Or if there are, they're all neutrally balanced out. So yeah. Well, let's make this a little more complicated then and look at the electric field just above the surface of that conductor. So not looking inside of it, but just outside of it, we have our sigma, our surface charge density, which is going to be our charge that's enclosed, is that density times the area. So kind of keep that in mind. This takes care of this left side of the, or the right side of the equation. But the left side, what do we need to do for that one? Yeah, draw a Gaussian surface. So when we draw our Gaussian surface, we have a couple different options here, which is kind of fun. We can do option 1, which puts one side inside of our conductor and the other one outside of it. When we do that, the one that's inside the conductor here ends up canceling out with 0, or the one on the top side ends up having an electric field traveling through it. What does that mean? We have just our EA term here. We have our charge density that we solved for previously for Q. And what do you know? These areas actually cancel out. So that's really cool. When you use our Gaussian pillbox for planarly symmetric surfaces, sometimes this, or not sometimes, quite often, the area term is just going to end up canceling back out. What does that mean? Our electric field for a conductor or something that has 2 charged surfaces is going to be our sigma over epsilon naught, or that's our answer when we plug our numbers in. But I said this is option 1. Why? Because the other option you could do is draw this Gaussian surface. And this one's just as good. When you do this one, we extend it on both sides equidistant, but now we have 2 areas, this bottom area and this top area. So this left side is going to have 2 different area terms. That also means that we're going to have 2 charges enclosed. It's not just the top surface that has charge now, it's the top one and the bottom one. So because that's the case, this 2A and that 2A end up canceling, and we get the exact same thing. So you pick your journey that you want to go on for this problem, but whether you do the single one inside or the 2 on the outside, they both work just fine and will get you to the same place as long as you keep track of where the charges are located. Well, what if we have an insulating plate instead? Same surface charge density. The main thing is it's not 0 inside, the electric field is not 0 inside that insulating plate. So what's the electric field just above it? Just like before, we have our thing here. We put our charges all across the surface so we can find what our charge would be. It's our charge density times that area. And when I look at the left-hand side, how do I solve for that side? Yeah, we're going to draw our Gaussian surface again, just like we did before. So same kind of process, whether it's insulating or conducting. But now this time, because it's an insulator, we only have one option. And that one option is to extend it on both sides of our thin plate. Why? Because the E field's not zero inside, so that first case wouldn't really apply here. When we do this, we have our two surfaces that have, for our Gaussian surface, for our pillbox, for the end caps that have some contribution. Remember, the sides don't contribute because at all points on the surface, the electric field is parallel to that surface. So that's the case. We now have to look at our charge enclosed. Well, we only put charges on the one side of our insulating plate because it's an insulator. It didn't distribute to both sides. So because that's the case, this time we only have one single area term A, and that's going to make it balance out this time when we cancel out our areas to give us sigma over 2 epsilon naught, or a 1.3 times 10 to the third newtons per coulomb. So you might notice a drift here. And here's the main thing I want you to take away. For conductors versus insulators, we know conductors have zero electric field inside of them, where for insulators, that's not the case. We can use that to our advantage in how we solve them. And the main thing, when you add to a conductor, charges go onto both sides of the plate, essentially making it so there's charges on two surfaces. That's different than an insulator, where the charge only goes on the one surface. So if we look at a given surface, it doesn't matter actually how close you are to the surface. Why? The same lines are going through our areas, no matter how close or far away we are, because we're that parallel. So for a conductor, it's going to look like this. For an insulator, it might look like this, where the only factor, which is the main thing here, is the electric field, is the surface charge density, and indirectly the material. If you have a more dense charged surface, it's going to increase your electric field. If it's a conductor versus insulator, those are also going to behave differently. So let's look at one final practice example to kind of apply this and send it home. For an insulating plate with uniform charge density, insulating, so that's always fun, 2 centimeters thick, I want to know what the electric field is going to be at a couple different places, 0.7 from the center and 6 centimeters from the center. I know that because it's all uniform, at the very center line right here, my electric field is going to be 0, just because I have the same amount above and below that point. So this is the only spot that exists. Here, any other level, it wouldn't be that case. So when we solve for 0.7 centimeters from the center, we're going to be inside of this block. We're looking at our total charge, which is going to be enclosed inside that area there. So it's my total charge, Q, which is my volumetric charge density times that total volume. What's that volume going to be? It's going to be my area of the base times the height, where the total height of that surface is going to be 0.7 centimeters, or sorry, 0.7 plus 0.7 to give us 1.4 centimeters total. And that's what gives us here this 0.014 meters. So when we plug that volume term in, we have our charge density times our volume. We have our two different surfaces on the left-hand side, our E times 2A. Our areas end up canceling just like before. And if we solve this thing through, we're going to get about 18 newtons per coulomb. So calculating this one. When we hop on the outside, this is what looks something like this. Here's where it gets a little bit tricky. When we're on the outside of it, I end up having, this is the only region that has charge enclosed. So a lot of times the most common mistake students would make is instead of doing the 2 centimeters that I have listed here, they would think it's the entire, what's that going to be, 6, 12 centimeters total. And that's not true. It's only the 0.2 because that's the only place where the charge is enclosed. So once again, making our substitutions where we have our charge density times our volume, our areas of our end caps are going to cancel just like they did before. And when that happens, we're going to get our 26 newtons per coulomb. This is a quick example of how we can solve with an insulating plate. So what should we take away? The main thing to take away is what these different density terms are referring to and how we use the Gaussian pillbox, where the flux only occurs through the end caps and not through the sides due to the fact that it's either parallel or perpendicular to those surfaces. Also, don't forget that conducting and insulating surfaces behave differently. So if the problem says it's an insulating this or a conducting this, you need to immediately jump to how it's going to be different to keep track of those issues. With that said, I look forward to seeing you at the next couple of videos. We're going to explore cylindrically and spherically symmetric surfaces. See you then.